Okay, great. So then, yeah, we have our next speaker, which is Florian Meier from TiQT, and he's going to be telling us about fundamental resolution trade-offs for timekeeping devices. Please take it away.
Yeah, thanks a lot for the conference, Mark, and all the other organizers. And it's nice to see so many new but also familiar faces. So to those that I haven't met yet, I'm Florian Meier, working at the group of Markus Huber in Vienna. And in my PhD, I am working mostly on the thermodynamics of timekeeping. And for the next 30 minutes, I will tell you parts of this work, and we'll try to investigate what are some of the ultimate limitations of the accuracy of clocks. So before we are even in a position to start talking about those ultimate limitations, we have to somehow get a clear understanding of how to measure such a performance, the performance of a clock in general. And the best way, I think, to understand these performance measures of clocks is to experience it firsthand. So what we'll do is a brief experiment that some of you will already know. And the experiment we'll do is that you as the audience will play a clock, and I will measure your performance as a clock. And the performance measures that we will be using for this experiment is a selection of those two. So one of them is the resolution of a clock. So if you have a clock, and I think now I don't have to convince you of this anymore, if you have a clock which produces a sequence of ticks, somehow the average time between those two ticks is a relevant figure of merit that characterizes how useful this clock will be to solve in a certain task. Then another figure of merit is what I'll define to be the accuracy, and it is the number of times such a clock can tick until it is off by one tick on average. And somehow for both of those performance measures, you need a reference time, and I will assume that there is, for this experiment, some perfect reference clock, and I will use my cell phone to measure your performance as a clock. So with that out of the way, I'll quickly try to explain how the experiment will go. So you will be a clock that ticks every second, and the ticking of the clock will be done by clapping into your hands. And you will be a kind of collective clock, so I'd say we start with Michael, and then Jared Wilburn, then Mark, and it will go around like a snake, and once you're off by 1 second, I'll just say stop, and then we know resolution 1 second, and accuracy however far we go. Everything clear? So I will do something like 3, so that's not yet the run, but 3, 2, 1, and then on 0 you go. So you have some gauge as to how long 1 second of my cell phone is. 3, 2, 1, and stop. So I would say it was around 3.5 that we were off by 1 tick, and I assume I can also use this here. So the first run of the experiment, we had a resolution of 1 divided by 1 second, and an accuracy, so number of ticks, was roughly 3 plus minus 1. So I was told that the error bars are important in the last version of this talk. Now, that's one round. And somehow I told you that this talk is about limitations of these performance measures of a clock. And now we'll try to modify the clock slightly such that we can increase this accuracy. And the goal here is that we keep the underlying clock the same. So you will again tick in 1 second intervals, but now the game we play is that actually only every second tick counts. So the resolution goes down to 2 seconds, but we'll see what happens to the accuracy. So how many of those 2 second ticks can you do until you're off by such a 2 second tick with respect to my cell phone clock?
But we each still count for
Exactly. The underlying clock dynamics are precisely the same.
One clap or two claps?
So let's do so.
this is only
You'll do a loud clap, you'll do a silent clap, loud clap, but I'll be able to post-process. You ready? Okay, then we do again. 3, 2, 1. And off. So, so now we have to count like only every second tick, but that makes 1, 2, 3, 4, roughly 5 ticks that you manage to get the right way. So the second experiment, we somehow noticed that for this 1/2 second resolution clock, the accuracy was something like, what did I say? 5 plus minus 1. So we managed to get an increase in accuracy of this clock by lowering the resolution. And that's the recurring theme that we'll encounter throughout this talk. That somehow in order to increase the accuracy for fixed physical dynamics, here you as the clock were fixed at 1 second, but we now count only 2 seconds, the resolution will go down. The outline of these next, I think, roughly 20 minutes will be such that I'll introduce some basics, basic concepts for clocks, which has been drastically simplified by the talk of Jared Milburn before, so that we can then, in the next step, go to a more rigorous mathematical framework and then state a universal trade-off relation between what we call accuracy and resolution of clocks. And finally, we'll draw some conclusions and then head off for the lunch break. So, what do all clocks have in common? And one example is the atomic clock that we've extensively heard about before, and it uses a laser to work. And the coherent oscillation of the electromagnetic field in itself doesn't yet tell you, for example, it's, 3 minutes have passed, you now have to turn off your oven. It's somehow a discrete counting mechanism that you have to engineer that uses this coherent oscillation to produce ticks, and these then allow you to tell how much units of your time have passed. And the same also goes for a grandfather clock, where you have an oscillation of a pendulum, but this itself is not yet what tells you how much time has passed. It's the escapement mechanism together with the clock counter that tells you what time it is. And the question we'll investigate now is somehow what is the most elemental primitive of a clock that we can use to track time. And there, the thermodynamic perspective is important. So the second law of thermodynamics dictates that all these clocks produce entropy and use out of equilibrium resources to produce those ticks. So we have this thermodynamic irreversibility, and we have these discrete ticks. And the simplest system that we can work with is a two-dimensional, two-state system, and we can ask ourselves, how can we get a clock out of this two-state system? And for simplicity, I'll label one of the states as the no-tick state and the other as the tick state. Now in a very abstract picture, but the idea is that initially our clock is in a no-tick state, and then for this system to act as a clock, it should somehow change from the no-tick state over to the tick state, and you can tell now some unit of time has passed of this clock after it is ticked. To treat this example more, mathematically more rigorous, we have to make a couple of assumptions. So if you have some physical system that goes from one state to another, and this happens in a thermodynamically reversible fashion, you need interaction with an environment. And one assumption that I will make throughout this talk is that these interactions are memoryless. And that's not, fundamentally necessary, but we do this out of mathematical convenience such that we can easily treat the system with a Markovian master equation. Another assumption we'll also do throughout the talk, and that's more physically motivated, is that we don't want any time-dependent driving. So somehow, if we have again this two-state system, it shouldn't depend on some background parameter time when this transition happens. So all the interactions should be independent of some parameter time t that we introduce in our equations of motion. And now that we have the assumptions for the mathematical model, we can go through the calculation, introduce a random variable describing the tick time and get tick distributions. And for this most elemental example from before of the two-state system, we get exponential decay at a given rate gamma that describes the time scale of the overall evolution. Now, that's quite a bad clock, but in general, if we look at those ticking clocks that produce ticks, we can generally define a tick probability density that describes the distribution of these ticks with respect to parameter time, and you can calculate average and variance of this time of arrival between two ticks. And these two quantities you can calculate and define again something like a resolution as the inverse average time coinciding with what we had before, and you can also define an accuracy as the signal to noise ratio, so mean squared divided by variance. And it turns out that if you have a sequence of independently and identically distributed ticks, this accuracy defined as that ratio coincides exactly with the definition at the beginning. It's the number of times the clock ticks until it's off by one on average. So let's quickly talk about the significance of those two figures of merit that we introduced. The resolution is somehow a time scale dependent quantity. So by just changing the time scale, you can somehow make the resolution as a figure of merit ambiguous, but still, in any operational setting, the resolution as a quantity to quantify the performance of the clock is physically meaningful, because you can, for example, compare two clocks with two different resolutions, but the same accuracy, say hypothetically 10 to the 4, and the one clock that ticks every second is for practical purposes much more useful than a clock that ticks only every 10 million years or so. So the key thing that we want to make here is to fix some time scale in our discussion, and for our purpose this will be the decay rate gamma that we fix. So for every clock that you build, you have some time scale that you fix so that you can calculate those figures of merit. And once we do this, we can go to the next step and ask ourselves, what do we even want? And that's, of course, a clock with high resolution and high accuracy. And the question is, of course, can we really get this? Are there any limitations to increasing those two numbers? And this is what we'll get to now. So we start with a brief illustration of roughly the clock we had at the beginning, and there is one scheme that we can do to improve the accuracy of a clock. So we start with some clock tick sequence. So the x-axis is parameter time, and those vertical stripes are the ticks of this hypothetical clock. And now one scheme to improve the accuracy is to just summarize every two ticks into a new tick. That's exactly what we did before. You get a new sequence, and if you go through the calculation, assuming the ticks are IID, then you find that the accuracy doubles, but the resolution is divided by 2. You can do this more generally for summarizing n ticks. The accuracy increases n-fold, but the resolution is also divided by n. And you find an inverse linear relationship between accuracy and the resolution for this specific scheme. And there is one important aspect as well to notice here is that suddenly the thermodynamic cost of those new summarized ticks is greater than that of the ticks before, because you suddenly have n irreversible events for such a higher accuracy tick. So the question is whether we can do better than this particular scheme. And as an example to illustrate the idea how to go away from this averaging, we can look at an hourglass. So the standard way of using an hourglass is exactly averaging. So one can think of the individual sand grains dropping down as those elementary ticking events, but no one uses, say, such a sand clock to brush your teeth by just counting the individual sand grains, but rather you just say, okay, I start brushing my teeth when all the sand is on top, and then I stop when everything is at the bottom. Now, As we discussed before, this gives us some inverse linear relationship, but what we could do instead is the following. So we start with the distribution of the ticks of the sand grains dropping down, but what we add now is a rotating wheel to this whole mechanism. So we have a wheel that has a hole perforated into it, which rotates at a fixed frequency, and whenever the hole passes between the opening of the two glasses, the sand grain is allowed to pass through. So now instead of just summarizing ticks, we suppress them. So this gives us some temporal modulation of when the sand grains are allowed to drop between the two glasses. And if we say go through this schematic picture, what we find is that the accuracy can scale inverse quadratically with the resolution. But there's a couple of very important caveats here. For this very conceptual model, what is exactly this rotating wheel? How much does it thermodynamically cost to rotate the wheel itself? And those are some of the questions that we have to answer if we want to use this scheme of temporally modulating the probability of the individual ticking events, if we want to have a thermodynamically consistent picture of the cost of timekeeping. And to do this, we go back to our two-level system from the beginning and try to extend this to a model where we can get exactly this temporal concentration of probability, but in a model where we can account for the thermodynamic cost of doing so. So we promote the two-level system we had from before to a quantum system, and what we have is an unstable two-level system that if it's prepared in the top state, it can decay, emit a photon, and that's what we define as a tick in this picture. The modification allows us to somehow embed this system into a larger Hilbert space, maybe make a ladder out of it, and in general the whole system, the clockwork, can interact with the environment through some stochastic jumps. And if the two-level system decays and emits a photon, we will count this as a tick. That's this more general picture of a clock in stochastic thermodynamics that we can draw, satisfying the assumptions, memorylessness and no time dependence we had before. Writing down density matrices for describing the system with proper equations of motions, we can write the clock state as a sum of not having ticked, of having ticked, and in general we can add arbitrary number of ticks, but the picture doesn't change qualitatively. So we get the set of equations of motion under the memorylessness assumption. That's essentially a Lindbladian master equation. What I want you to take away from this is not memorizing the equation of motion, but rather that all the terms that appear in this equation have to be time independent in the sense that they don't depend on the parameter time that we have there. And that therefore the clock model we have here does not depend on some external driver. So this is kind of the universality class of clocks that we are talking about, and they define ticks by this stochastic photo emission that is temporally modulated by the additional dynamics we have in the system. And we can calculate the ticking probability as by taking appropriate traces, but also this formula, it's important to take away that one can calculate these ticking distributions by solving the equations of motion. Most importantly, for this model, if we look at the accuracy and the resolution, so we calculate this by calculating the tick distribution, we find that for all clocks whose ticks are generated by memoryless stochastic processes, that the accuracy is always upper bounded by the resolution inverse squared times the time scale gamma of this stochastic process that we have. What this result tells us is if we look at the say, two-dimensional plane of clock performance, where we have the accuracy on the y-axis and resolution on the x-axis, is if we fix the time scale, there is suddenly a forbidden region which we can never achieve. And all clocks with their performance have to lie somewhere within this green allowed region. And now that we know that we can't achieve the best of both, so we can't go to the top right, we somehow have to ask ourselves, what's even achievable. And for that, we take again our two-level system, and it turns out if we want to lie exactly on this boundary line, what we need is a perfect external clock controlling our system. And the reason why that's the case, and that's also somehow the illustration of how to prove the statement, is if you want to have this perfect accuracy resolution trade-off, what you need to do is you keep this two-level system in the ground state until the time where you want it to tick, and then through some external control, you instantaneously excite it, and then the exponential decay generates your tick. But that's obviously cheating and requiring external timing resources to achieve exactly this trade-off relation. So, knowing that that's not possible, we ask ourselves how to achieve it, and what's the cost of achieving, say at least asymptotically reaching this boundary line. And for this, we again take our model, but now if we want to account for thermodynamic costs, we say that these general Lindblad dissipation contributions have to be thermal, so we are only allowed to couple our clock to out of equilibrium thermal baths, and this allows us to calculate the entropic cost of running such a clock. And there it's an open question of what exactly is the relationship of what's the thermodynamic cost of getting a certain accuracy resolution pair. But one specific example, okay, so yeah, one specific example that we can look at and that illustrates the thermodynamic cost of generating these ticks is such a three-level thermal clock that essentially consists of a thermal machine and this unstable two-level system that generates the ticks. And the idea is that this two-level system is, as from before, the system whose decay generates ticks, but now instead of having an external agent that keeps it at the ground state and suddenly excites it, we use an autonomous thermal machine to coherently drive up this excitation. And for this, we couple the thermal machine to out of equilibrium heat baths, which essentially pump up this, or give a population inversion of this two-level system. And what we see is, instead of an exponential decay behavior, the exponential decay is slightly delayed through this temporal concentration of probability that happens with the thermal machine. And this is exactly the idea of improving the accuracy using only thermal resources. And with that, we are already approaching the end of this presentation. And I'd quickly like to summarize the key ideas that we covered all in all. And this was that some of the key ingredient to timekeeping is that these clocks are produce ticks, and they produce them in a thermodynamically irreversible fashion. And taking this as the ground step, we found that if we calculate an accuracy of this clock and we have this stochastic tick generation process, that the accuracy is always upper bounded by the resolution squared. And then it's an open question at the moment, what exactly are the achievability relationships of this trade-off when looking at the thermal resources that one has to pay for building such a clock. And with that, I have some shameless advertisement. If someone wants to look at the preprint, here is a QR code. And in that case, I think thanks a lot for participating in the experiment and joining this talk.
Thanks, Florian. So yeah, time for questions. Go.
Yeah, great talk. So the N-level system that is came is suggestive of super-rating emission in collective system of dipoles. Have you thought about that as a possible physical realization?
So,
of the ticking mechanism?
Coincidentally, that's actually something that we are working on at the moment. So there, the difference between the picture I just showed to you before and that super-radiance is that super-radiance will be the collective emission of many photons. So the definition of a tick as a single photon is, say, doesn't apply straightforwardly, but you could, for example, use this as an amplification. process, or define the photon as the last photon. So there is some ambiguity on how to use this as a clock, but I think exactly the phenomenon of superradiance has many of, say, desirable properties for building a clock with high accuracy.
NIST is actually building super-radiant clock.
Oh, this I didn't know. That sounds exciting.
Yeah, it is. It should be good clock.
Yeah.
More questions?
Thanks for a very engaging talk. Yeah, okay, maybe I'll just ask one of my questions. The other is more relativity related puzzle, so we can chat after. But I'm curious. You mentioned you focus on Markovian evolution. Yeah, I mean, we are all aware that that's doable. But I was wondering if you have any intuition about the possibility of describing non-Markovian processes. And I mean, the reason why I'm asking is that many of the experimental setups that people are using in the lab, they do display non-Markovian. So yeah, I would be interested to hear that's something. I mean, if you think these relations will not hold, like to which extent you think the results will be different?
So the key, say, part that would change if you suddenly have non-Markovian dynamics, if you use it in the driving of the clock, then it doesn't affect this trade-off relation. So the place where it will affect the trade-off relation and possibly even the definition of what you define to be a tick is when the photoemission, which you count as a tick, if this is not a memoryless stochastic process anymore. So there one would even have to think about how do we even define this time of arrival in that case. But I haven't worked on this, but this would definitely be a very sensible extension and question to ask for this model.
Thank you for great talks. I'm very interested in the relation between that equation and that inequality and thermodynamics uncertainty relationship. Because in thermodynamic uncertainty relationships, variance divided by the mean of 0 is bounded by the dynamic activity. And this dynamic activity can be regarded as a timescale persistent. So is it possible to, so I think that such kind of simple system, for such simple exponential system, it is possible to obtain a calculate dynamic activity. And then, and I want to know the relationship. So have you ever considered that relationship between that inequality and thermodynamic relation?
So on a, say, case-by-case basis, we've looked at this already, but somehow finding such a, say, universal trade-off between this fraction that we call as accuracy and dynamical activity, to my knowledge, doesn't exist yet for open quantum systems evolution. I mean, universal in the sense that it's independent of the specific Hamiltonian that you choose. So one caveat that one would have to think about there is that here in this picture we have the time of arrival of the photon. So this stochastic tick counting process is fully reversible. So going into this, going into the realm of thermodynamic uncertainty relations, you would usually have a bidirectional, so a current with asymmetric weights. So the definition of tick time would have to be adjusted to, say, be in the same framework as the TUR. But this would definitely be, so this would be an extension of this trade-off relation. But then one would also have to generalize this inequality exactly to those reversible currents that appear in the setting of TUR or KURs.
I mean, if I may, we've discussed this before, but I think this is very closely related to the KUR for kinetic uncertainty relation for first passage time.
Yeah.
Because I think that I mean, the variance of first passage time is directly connected to the accuracy. The gamma that appears in that bound is essentially connected to dynamical activity. It's a kind of conditional dynamical activity. So I would say they're very closely connected.
Yeah, yeah.
But they're not the same, you say, or same.
Exactly. They are very closely related, but in the sense that in the definition of those individual terms, you would have to account for the reverse thermodynamic process that.
But not for the kinetic uncertainty. I mean, you don't need to have. You don't need the balance for that, I don't think. But, okay, but I guess we can discuss this more later.
Yeah, I'd be very happy
Yeah,
to
yeah,
discuss.
Gary, last question. Yeah, go for it.
I'm a little bit confused about what you call exponential fit. I mean, is it that it's a renewal process such that a jump completely resets the state of the system? Or is it that the waiting time distribution of the thing really has to be an exponential? Because the latter is very restrictive.
Okay, it's right that the way it's written there is a bit ambiguous. By, say, this exponential thinking mechanism, I mean that so in the end, what is meant by this is that you have a time-independent term in the Lindblad-Master equation. So the better way of putting this would be that we have a Markovian jump process. But yeah, if you look at the ticking distribution, now here I think I only sketched it roughly, but this is the integrated ticking distribution. You see that it is with the overall dynamics, not exponential anymore.
But do you have to assume anything specific about the jump operator, or it can be for any kind of?
It can be an arbitrary jump operator, which is time independent.
Okay, I think probably more questions, but we can postpone the lunch, so thanks, Florian.